Hey everyone. So in this last video, I'm going to go back through our R example to show you how to program your own OLS estimator using maximum likelihood. Okay. We will go through the same example that we talked about in the previous kind of R coding video, as well as in our Q&A session, which just focuses on the relationship between recent growth in personal income in the United States and how it's associated with the incumbent party's vote share in US presidential elections. Of course, with the hypothesis being that the larger economic growth and the more, personal income grows in the previous period, the more the larger the expected vote share of the incumbent party, as the incumbent party is rewarded for their economic performance. Okay. So you've seen this example before. We're loading the same data, and we're basically just replicating this same basic bivariate regression. But now we will approach it from basically this idea of maximum likelihood, and we'll see if we get to the same result as in the previous video when we just kind of computed our OLS coefficients based on minimizing the sum of squared residuals. Okay. So the first thing we have to start with is we have to write the log likelihood in R as a function. Okay. And I mentioned before that we can characterize the log likelihood as this sum, which again is based on this assumption that each individual observation is drawn from a normal distribution, and we have, the density of the normal distribution is basically determined by the observed data, but then also our beta and sigma parameters. Okay, we have our observed data, we have our x and our y, we don't have our beta and we don't have our sigma, and the goal is then to find the parameter values for beta and sigma that are most likely to have generated the data. Okay. So programming or basically translating this log likelihood function into our code, what we'll do is we'll create a new function called log likelihood. This is a function with 3 arguments. We have theta as just the set of all parameters that we are trying to estimate, that we're trying to find the maximum likelihood estimate for. We have our y, which is the vector of outcome values, and we have x, that's the matrix of independent variables plus a column of ones for the constant term. Okay. There are a few kind of R programming steps that we have to go through in order to be able to maximize this log likelihood function. The first thing is we want to take this theta and split it up into 2 parts. One is a vector of beta coefficients, and the second one is gamma. Gamma is just a placeholder. Ultimately, that will turn into our sigma squared. Okay. So while we have here one argument which kind of contains all the parameters that we're trying to estimate, we're splitting them up into 2 different parts. One is beta and one is this gamma. Okay. And this is just by separating this theta vector into 2 parts depending on the number of variables that are included in X. Okay. Then, of course, sigma squared is a variance parameter. And we have to make sure later on when we try to kind of numerically optimize this function, we have to make sure that this sigma square is always positive, because R by itself, as it tries to maximize this function, won't know that sigma square is a variance, and the variance always has to be positive. So in order to do that, we're basically taking our gamma and we're taking the exponent of gamma. Okay, so the exponent of gamma will then be equal to sigma squared, right? So while we use sigma squared in our likelihood function, ultimately what the function will plug in is different values of gamma. These values of gamma, they're not constrained. They can be from minus infinity to plus infinity, but then we're taking the exponent of that gamma, so it's always a positive value, and that positive value is then used as our sigma squared, okay? So this is just kind of to make the optimization later on work. Then the next thing is we have to compute our residuals, epsilon hat, and that's just y minus x times beta, based on the data that we observe. And then we compute the log likelihood for each individual or each observation. And this is just plugging in these individual, plugging in kind of this function or this equation in R, okay? So we have minus 1/2 times log sigma squared minus epsilon hat, that's the residuals, squared, divided by 2 times sigma squared, okay? So that's just the equation that you see exactly up there. And that's the likelihood contribution of each individual observation. And then, of course, to compute the entire likelihood function, we have to sum this across all individuals, and we do this by using the sum command. So we sum across all observations and across all kind of likelihood contributions for each individual observation, okay? So now, after kind of setting up this log likelihood function, we can plug in different values of theta, which includes our regression coefficients and sigma, as well as our y and x, so our actually observed data, okay? Again, we want to prepare our data by saving our dependent variable as y and our x, our independent variable, including the constant, as x, okay? And now, kind of to get an idea of what this function ultimately does, we can just plug in different numbers. And note we have 3 different parameters that we're trying to estimate here. 2 regression coefficients, 1 constant, 1 slope, and then 1 scaling parameter, which is just the sigma squared, just the variance, essentially, okay? So we can plug in, for example, 0, 0, and 1, which would be, you know, an intercept of 0, slope of 0, and a variance of 1 with our y and our x. And all this function does is then provide a likelihood value for that specific set of parameters, okay? So this is basically just plugging in these values for beta, for sigma, for y, and for x, and then computing the sum, and the value that we receive is minus 8,069. You know, that value itself doesn't really tell us all that much, but what we know is that this value is proportional to the likelihood of a given theta conditional on the x's and the y's that we observed, okay? So that means we can plug in the y and the x is, of course, what we observed. We keep that constant, but we can plug in different parameter values for beta, for sigma, and we get different numbers. And it turns out the higher the number, the larger this number. This is now minus 2,000 for an intercept of 20 and a slope coefficient of 1. The larger this number, the larger the likelihood of these parameter values to have kind of generated that data, similar to the example of the probability of appointing a female Supreme Court justice to the Supreme Court in our previous example, okay? We can, of course, you know, plug in different values and play around, and you know, we'll see that eventually we get to values around, you know, minus 28.3. That's pretty close to, of course, I plugged in values here that are kind of consistent with the OLS coefficients that we estimated earlier, but we can see that the closer we get to those OLS coefficients that we estimated earlier, the higher this likelihood function, or the higher this likelihood value gets, okay? So kind of similar to the Supreme Court example that I showed you, where we just had one parameter and a very simple likelihood function, we can also plot kind of this likelihood surface for different parameter values, okay? And the way I do this here now is, what I'm going to do is I'm going to look at a sequence of possible values for the intercept between 35 and 55, and possible values for the slope coefficient. Here I'm looking at values between -2 and 8. Holding now, just assuming that we knew the correct error variance, we're just holding that constant. And what I'm doing here is I'm just creating a quick tibble for basically a grid of possible values for beta 1 and beta 2 for the intercept and the slope, and computing the likelihood function just the way we did it here, but more systematically, kind of like a grid search of possible values for both beta 1 and beta 2, okay? And we can directly plot that likelihood surface for these different values. And what you see here is on the x-axis, we have our different values for beta 1, ranging from 35 to 55, and our beta 2 ranging from -2 to around 8, okay? Or should be around 8, yes. And the colors here, the further we go towards yellow, the higher the values of this likelihood function that we return, okay? So we can basically kind of, if we wanted to see now, if we wanted to find now the maximum likelihood estimate, the same way we did it kind of graphically in this Supreme Court example, we could kind of do a grid search like that and then say, okay, well, looking at this kind of likelihood surface, the most likely, or the parameter values that maximize this likelihood function are probably somewhere around 2.5 and 45, or maybe 46 and 2.6, or something along those lines, right? Of course, we will not do this graphically. We can ultimately use R to kind of do this numerically, because there are a lot of algorithms that help us kind of optimizing these types of functions, but this kind of gives you an idea of what this likelihood surface actually looks like for, in this case, a 2-parameter problem, assuming the scaling parameter already taking kind of the correct value, okay? We can also, and this we will later on in the upcoming weeks, look at kind of posterior samples from the posterior distribution, where we talk about kind of covariances between parameters, and you kind of get an idea about how these parameters are kind of correlated based on the shape of this likelihood surface as well. But we'll talk about that more as we proceed throughout the semester. The point is now kind of the last step, rather than doing this just graphically and looking at the likelihood surface and kind of finding or eyeballing what the most likely parameter value is. We can of course use algorithms in R to actually optimize the likelihood function. The way we're doing this here is we're selecting 3 starting values, which we're just drawing from standard normal distributions, and then we're using the optim command with the set of starting values that are just random draws from the normal distribution. The function is the log likelihood function that we just programmed previously. We have our y and our x, which are the data that we observed that are also plugged into this log likelihood function. We're also specifying that we want to actually maximize this likelihood function. If we didn't include this argument, this would find the minimum, which is of course not what we need. We also tell R that we want to include the Hessian matrix, because we want to compute our standard errors, and we're using BFGS as the maximization algorithm. There are other algorithms out there as well, but this is not really the focus for us right now. This is just one algorithm that works fine in this simple example. And if we look at this result, we get a couple of pieces of information. We get the parameters. Those are the point estimates on this likelihood surface that maximize the likelihood function based on the BFGS algorithm. We also see the value of the likelihood function at that specific point, which is -28.1364. So the the other value that I plugged in was already pretty close, and we have a couple of other additional information about convergence and so on that we don't have to worry about too much right now. The key point is that we can again go back and compare this to compare now our kind of custom maximum likelihood estimate to the pre-packaged LM function to kind of confirm that what we're doing using maximum likelihood techniques kind of conforms with the basic linear regression. Okay, again, we're just estimating a basic linear regression with vote as the dependent variable and growth as the independent variable, and then we'll just create a tibble that combines both our maximum likelihood coefficients as well as the OLS coefficients based on this model, as well as the standard errors. Note here that the maximum likelihood, the standard errors based on the maximum likelihood estimates are based on, as I mentioned in the previous video, based on the Hessian matrix, which again is the matrix of second order derivatives of the likelihood function at the maximum. So it tells us something about the curvature of the likelihood surface. We take the negative of that Hessian and then take the inverse. So the negative, that's the information matrix, and then we take the inverse to compute the variance covariance matrix. If we take just the diagonal of that covariance matrix and take the square root of that, that will give us the standard error based on the Hessian matrix. Okay, kind of if you kind of want to go back to the previous video to kind of remind yourself of the steps to get from kind of the curvature of the likelihood surface to the actual standard errors. That's basically just what this code is doing. To get the standard errors based on our regression model, we can just take the diagonal of the variance covariance matrix and take the square root. So this is kind of the equivalent, okay? And we see that our maximum likelihood estimates, our maximum likelihood coefficients that we kind of derived, just based on the formula, are exactly equal, or they don't have to be exactly equal because the numeric these optimization algorithms are not not always perfect depending on the starting values and so on. But in this case, at least, we get the same results for our intercept and our growth coefficient. The standard errors are slightly off, but overall we can see that the OLS coefficients and the maximum, or we can basically get the same coefficients, estimate the same parameters using maximum likelihood as we have using kind of just ordinary least squares. Okay, so that concludes our coding example. I'm looking forward to our Q&A session on Monday.